Hello, everyone. Welcome to the HPL seminar this week. It is my pleasure to introduce today's speaker, Michael Baggaley. Michael did his undergrad at Mercyhurst University in Pennsylvania, the United States, and achieved a Bachelor's of Science degree in 2011. Then, in 2012, he started his master's course at the University of Kentucky under the supervision of Dr. Michael Paul. His research was specialized in the field of biomechanics, specifically working on how hip structure and strength are related to the lower extremity kinematics on the frontal plane during treadmill running. His passion in running biomechanics further led him to start a PhD course here at the University of Calgary in 2016. He is currently working on muscular skeletal loading during graded running for his thesis project under the supervision of Dr. Brent Edwards. He also has work experience as a lab manager for 2 years at the East Carolina University, where he was responsible for providing students training on how to use the lab equipment and how to collect data. He also organized a science outreach events where he invited over 40 high school students to the lab and gave a demonstration on how biomechanics plays a role in our lives. He mentioned that this event has become one of the scientific accomplishments that he is most proud of. Aside from his academic career, he spends as much of his free time outside by trail running, backpacking, and biking through the Canadian Rockies. When Michael is not outside, he can be usually found in kitchen, baking, or cooking vegan delights. Today, he will be talking about part of his thesis project entitled as Internal Tibial Moments During Graded Running. Whenever you're ready.
Okay. Thank you for the introduction, Songwon. Okay, so we know that tibial stress fractures are a common running-related injury. They affect recreational runners, military personnel are two of the dominant groups who this affects. Tibial stress fractures are particularly deleterious to the health and well-being of individuals, since they require a long period of rest and rehabilitation to recover from. We know that tibial stress fractures are a fatigue failure injury, which means that they result from the repetitive loading and the accumulation of micro damage. Now, this micro damage is directly related to the stress and strain that the bone experiences, but the forces and moments that are acting on the tibia are an important factor in determining the stress and strain that the bone will ultimately experience. So, to convince you of this a little further, we'll look at this the normal stress equation, and I'll try to convince you that bending moments are responsible for the majority of the normal stress that a bone experiences. Now we can see in the equation on the left-hand side here that the normal stress is related to both a moment that occurs about the, in this case, the medial lateral axis, and also it's related to the peak axial force that the bone will experiences. So we can see this nicely on the diagram on the right-hand side, where in this case, what I'm showing you is how a bending moment about the x-axis in this case will cause tension on the right-hand surface of the bone, or let's call this the anterior surface of this idealized bone, and it would cause compression on the posterior surface, on the posterior aspect of this idealized bone. And then, like I said, it's also related to the axial force, where the axial force will just cause compression on all of the, on all aspects of the bone. Now, a similar equation exists for the shear stress that the bone will experience as well. And a nice study by Derek et al. Has highlighted the importance of bending moments in determining the peak normal stress. And in their model, they found that the bending moments were responsible for approximately 70% of the peak normal stress that a bone experienced. And even more so, the torsional moment was responsible for approximately 98% of the peak shear stress that the bone experiences. For those who are unfamiliar, when I talk about peak normal stress, what I'm talking about is what you see on the right-hand side in the image, where we have compression occurring on the posterior aspect of the tibia. This is represented by the blue colors, with the lighter blue shades representing areas of higher stress. And then you have the the tension occurring on the anterior aspect of the tibia, represented by the yellow colors there. So hopefully I've convinced you that bending moments are at least relatively important, are very important if we want to understand how the tibia is being loaded during locomotion. And to date, though, a lot of the studies have been focused on level ground running, and a lot is known about how the tibia experiencing stress, the stress and strain that the tibia experiences in a variety of different conditions. And these have been studied using both in vivo and in silico techniques. To be more specific, studies have investigated the effect of speed, stride length, step width, and running duration during level ground running. However, only one study has examined the effect of grade on tibia strain during running. And they actually only included 2 participants. And in the manuscript, they don't tell you what grade the individuals were running at or what speed they were running at. So this provides us really with very little information. But obviously graded running is a fundamental aspect of the sport, and you can't really get away from it. None of wherever you live, even in a place like Greenville, North Carolina, which is very flat, you still have to run up some hills occasionally. And graded running, while it's very similar to level ground running, also has some distinct differences. And I'd first like to focus on the differences in the lower extremity posture. So if we look at the image on the right-hand side, which has been adapted from a nice manuscript by Cassetarash et al., we can see that the black line image in the middle represents the configuration of the lower extremity segments during level ground running. And we first want to focus on the uphill running. These are represented by the gray lines. And in particular, let's look at the gray dashed line, which represents the uphill running condition at 10 degrees. And what we can see here is that the lower extremity is configured in more of a flexed position. And in particular, this is really highlighted at the knee joint, where you can see that the femur and the shank produce a far more flexed posture than in the level ground running condition. And opposite to this, if we look at the dashed black lines, and in particular, again, let's look at the very narrow dashed black lines, you can see that downhill running is characterized by relatively more extended lower extremity posture. And I think this is important because these changes in lower extremity posture could change how the forces are acting on the tibia during running. Graded running is also slightly different than level ground running in that it alters the ground reaction force variables, or some of the ground reaction force variables. And in particular, I want to highlight loading rate and the impact peak of the ground reaction force, since these have been identified as risk factors for tibial stress fractures. Now, if we look on the image on at the bottom, this is adapted from a study by Gottschall and Cram. They studied this presents the normal ground reaction force in a variety of uphill and downhill conditions. And if we start on the left-hand side of the diagram at the minus 9 degree condition, that really tall first peak represents the impact peak. And the rate at which that peak is achieved is the loading rate. And what we can see is in comparison to level ground running in the middle, downhill running is characterized by a much larger impact peak and a much higher loading rate. Opposite to this, if you go all the way to the far right-hand side of the image, you can see that uphill running is characterized by almost a non-existent impact peak and a much lower ground reaction force loading rate. And so some people would say that, oh, downhill running should be really deleterious to the musculoskeletal system because of these high impact peaks and loading rates. But I think it'll be interesting as we move through my presentation to examine if this is actually true. So I've hopefully convinced you that examining the internal forces and moments that are acting on the tibia is very important. It'll help us to get an understanding of how the tibia is loaded during running. And in particular, we really know nothing about how the internal forces and moments change as a function of running grade, despite the fact that graded running is fundamental to the act of running outside, or even on a treadmill for that matter. So in order to accomplish this, I brought 18 recreational athletes into the Human Performance Lab. This sample comprised of 9 males and 9 females. We had them run on an instrumented treadmill while we collected force and motion data, which can be seen in the image on the right-hand side. All subjects ran in 5 conditions, 2 uphill conditions at plus 10 degrees, plus 5 degrees, 2 downhill conditions at minus 10 degrees and minus 5 degrees, and 1 level ground running condition. All conditions were completed at a speed of 3.33 meters per second. And we had a variety of, a combination of forefoot strikers and rear foot strikers. Now, what I really want to get at is the internal forces and moments that are acting on the tibia. So how do I do this? Well, ultimately, in order to do this, what I want to get at first is the joint contact force. And in particular here, I'm interested in the ankle joint contact force, as this will allow me to then estimate the moments and forces acting on the tibia. But to get there, what I do is I take my experimental data that I collected, I run it through an inverse dynamics routine. This gives me joint reaction forces and joint torques. I then take some anthropometric measurements that I collected on the individuals, and this scales my base musculoskeletal model. The musculoskeletal model gives us muscle moment arms, muscle orientations, and it also gives us instantaneous force velocity and force length relations. This data is all important because in order to calculate a contact force, we know that it's the algebraic sum of the joint reaction force from inverse dynamics and the sum of all the muscle forces that are acting at a given joint. Now I don't have muscle force data, so I need to estimate this. In order to do this, we used a static optimization routine with a cost function that sought to minimize the sum of the muscle stresses squared. Each individual muscle force was constrained by upper and lower boundaries, where the upper bound was set by the instantaneous force velocity and force length relationships from our musculoskeletal model. All of our muscle forces were also constrained so that they had to replicate the joint torques that we measured experimentally. And at the ankle, our muscle forces were constrained to 2 degrees of freedom, flexion, extension, and abduction. At the knee, our muscle forces were constrained by 1 degree of freedom, flexion, extension. And at the hip, our muscle forces were constrained, so they had to replicate the flexion, extension, and abduction joint moments. So after all of this, I have a joint contact force. But that isn't enough. I told you again, I'm interested in the internal forces and moments that are acting on the bone. So we have to go one step further. But before I go any further, I kind of want to provide you with a bit of confidence in my modeling routine that, grade doesn't affect my estimated muscle forces. And in order to do this, I performed a similar analysis as other individuals where they've compared the EMG and the estimated muscle forces from our model. And in order to do this, I examined the cross correlation coefficient, which looks at the similarity of the 2 signals. And I also looked at the root mean squared error, which would give me a general idea of the error in newtons between these 2 signals. And on the top of the page here, I presented one of the better muscles. This has an R squared of somewhere between 0.8 to 0.89. So there's relatively good agreement between these 2 muscles. If you're interested in the RMSE for this muscle is approximately around 300 newtons across all grades. What's most important here is that there was no effective grade on either root mean squared error or cross correlation coefficient for any of the 6 muscles that we tested. But this is a really idealized scenario and it looks really good here. So if we look at one of the worst muscles, which is the tibialis anterior, you can see it doesn't do so well. And the tibialis anterior had a cross correlation coefficient of approximately 0.34 to 0.41 across all of the grades. But again, like I stated, there was no effect of grade on either of the 2 measures that I looked at. So there's, I think what we can ultimately say is we know that estimated muscle forces aren't great. We're not very good at predicting the individual muscle forces, but at least we can say that all of our muscle forces were equally bad across all grades of running. Now, we can get back to the question of how do we get our internal forces and moments acting on the tibia. So what I first need is a location of interest. And I've chosen on this diagram here, I've chosen to estimate the internal forces and moments acting on the tibia at a point that represents approximately the distal 1/3 of the tibia. And I've chosen this location because it's been suggested that this is, epidemiological research suggests that this is where a lot of stress fractures seem to occur. It's important to note in this image that these are anatomically correct axes. So we have one aligned with the axial component, one through the anterior posterior axis of the tibia, and then one aligned with the medial lateral axis of the tibia as well. So at the moment, we know where we're calculating our internal forces and moments, but how do we go about doing this? So on the right-hand side here, we have a very simplified model of the tibia. This represents some of the forces that are acting on the bone. Really, I've only represented a few of the muscles that originate or insert on the tibia. Obviously, there's a force due to gravity that's acting on the tibia. And like I said a couple slides ago, I'm going to be applying the ankle joint contact force in order to calculate these reaction forces and moments. Now, again, I just said I'm only interested in the distal 1/3 of the tibia. And what you'll notice between these two diagrams, what's nice and makes my life a little easier, is there's actually no muscles that originate below my centroid of interest, which is now represented by the black dot on the image there. So this means that I can eliminate these muscle forces. I don't have to account for them as forces that are acting on the centroid. It's important to note, though, that these muscle forces are already taken into account in my ankle joint contact force. So any muscle that crosses the ankle joint will already contribute to the the ankle joint contact force that this centroid is experiencing. But I don't need to account for the moments that any muscle that may, or that if it did, that would originate on this distal section of the tibia. So in order to calculate the reaction force, I simply took the inverse of the algebraic sum of the ankle joint contact force and the force due to gravity. And for the reaction moment, I took the inverse of the ankle joint contact force crossed with its moment arm from the point of force application to the centroid of interest. And same thing, I took the moment generated by the force due to gravity. So let's see at what we found. So first, I'm going to present the moment occurring about the medial lateral axis. And I think it's first important to look at the convention. So on the right-hand image here, we see the same image as I presented earlier. And what I want to highlight here is that a positive moment in this case would cause compression on the posterior aspect of the tibia. And if we go to our time series data on the right, that's what we see. But first, let me orient you to this image. So the black line in this time series data represents the level ground running condition, the red lines represent the uphill running condition, and the blue lines represent the downhill running condition, with the darker shades of each color representing the steeper grades. And so what we can see here is that both downhill running conditions had lower moments about the medial lateral axis than both the uphill running conditions and the level ground running conditions. This is quite interesting, but let's move on to another axis. And next we'll look at the anterior posterior axis. And again, we'll first start with the image on the right-hand side, where a negative moment would be causing compression on the medial aspect of the tibia. Same convention in my image. And again, this is what we see. We see medial compression acting on the tibia. And again, we see that the downhill running conditions are lower than the level ground running, but this time the downhill running conditions are only different than the +5 degree uphill condition. There was no difference between the +10 degree uphill condition or the level ground running condition or the other uphill running condition at +5 degrees. And finally, we'll investigate the torsional moment. So a positive torsional moment in this case indicates that there's internal rotation occurring at the tibia. And the torsional moment again was lower in downhill running in comparison to both uphill running conditions and also level ground running, and also the level ground running conditions. So this is all quite interesting. The data seems to suggest that downhill running is actually imparts lower bending moments on the tibia than either uphill or level ground running. But why is this? Why do the reaction moments change as a function of grade, and what is driving this change? Well, first, let's look at what makes up our contact force. So what we see here in this bar plot here is I've plotted the reaction force from inverse dynamics in the patterned bars, and the muscle force, my estimated muscle force from my static optimization routine in the black bars. And what you first probably notice is that the muscle forces are far larger than the reaction force from inverse dynamics, as to be expected. But what's more interesting and what makes sense if we think about our results is that the total muscle force, so this is the sum of all of the forces that contribute to the ankle joint contact force, is lower in the downhill running conditions. What's interesting though as well though, is that the total muscle force is actually lower in the +10 degree condition too, but this wasn't reflected in our changes in the bending moments. So there must be something else going on, and in fact there is. We see that there are actually differences in the contact force direction that are likely responsible for some of the changing moments we exhibited. Now on the left-hand side here, I've plotted the sagittal ankle joint contact force angle. And this angle is, this sagittal ankle joint contact force is composed of both the axial ankle joint contact force component and the anterior posterior ankle joint contact force component. And what we see here is that as you run downhill, you actually have a steeper sagittal plane ankle joint contact force ankle. So this means that more of this sagittal ankle joint contact force is being borne in the axial direction. And this is represented by the dashed black line in the image on the right-hand side. Alternatively, what we see when you run uphill is that the angle is actually a bit more shallow. So more of the contact force is being borne in the anterior posterior direction. And this makes sense if we again think about how I presented changes in lower limb configuration during downhill running, where during downhill running you have a more extended posture, and in uphill running you have a more extended posture. And this is important to highlight because this would directly influence the magnitude of the moment about the medial lateral axis. And this influences the moment arm that this sagittal plane ankle joint contact force would have with the about the centroid. And we can see this with this nice diagram here, where it makes sense then that we had these changes in angle. So despite the fact that we had lower total muscle force in the plus 10 degree condition, what I think is going on there is actually because the angle is becoming more shallow, more of the force is being borne in the anterior posterior direction. And this makes sense when we look at the image on the right-hand side, which presents the peak anterior posterior ankle joint contact force as a function of grade, where we see no difference between the uphill running conditions and the level ground running conditions, but we see that the peak anterior posterior ankle joint contact force is lower in the downhill running conditions. And again, this makes sense if we think about the results of the medial lateral bending moment, where we only saw a difference between the downhill running conditions and the others. There was no difference between the uphill running conditions and 0 degrees. So I've hopefully convinced you that there's many things that are contributing to this. It's not simply the muscle forces that are changing. Now, to take this one step further, I was interested in doing a similar analysis like Derek et al. That I presented in the introduction, where I modeled the tibia as a really simplified hollow ellipse, which you can see in the top image on the right-hand side. Now, I was interested in knowing how much, if my results are similar, where the bending moments contribute the majority of the peak normal stress. So in order to do this, let's say I'm interested in calculating the normal stress at the red dot, or the red star, and on the posterior aspect of the tibia. This is directly in line with the y-axis of the tibia. And in this case, for the hollow ellipse, we use a really simplified normal stress equation, where it's simply, again, due to the moment about the medial lateral axis and the axial force that's acting on the bone, along with some geometric properties of the tibia. Now, what we see on the image on the left-hand side is the compressive stress that's acting on this at this point in the tibia. And what we see, again, similar to the study by Derek et al., is that the bending moment contributes the majority of the peak normal stress that this idealized tibia experiences. And in fact, it contributes about 83% of the peak normal stress, which means that the axial force really is only contributing a very small amount to the stress that this bone is experiencing. And I'll take this one step further and do a similar analysis across the grades of running, where I'm going to use the same idealized hollow ellipse model, and I'm going to calculate the normal stress at the same position. And again, what we can see, I use the same convention as all of the other images. And we see that this makes sense. So now I'm taking into account this medial lateral bending moment that I already told you was lower in the graded running, but I'm adding in this small factor of the axial force. But we see a similar trend, where downhill running seems to reduce the peak normal stress that the tibia is experiencing by approximately 20 megapascals. Now, I don't want people to get too caught up in the absolute magnitudes of the peak compressive stress that I'm showing here, because they're certainly wrong. But I think the relative differences between the conditions are true. And I think this does suggest that downhill running is not as injurious as people might suspect. So what are my findings? Well, per step, downhill running seems to reduce the peak bending moments that the tibia is experiencing. It resulted in lower peak ankle joint moments. This in turn reduced the total muscle force acting on the tibia. And this was one part that changed how the bending moments were acting. But we also had changes to the orientation of the ankle joint contact force, and this contributed to reductions in the medial lateral bending moment during downhill running. In opposite, during uphill running, we saw no difference in the bending moments across the two conditions relative to level ground running. And this is despite the fact that we had a total lower muscle force in the plus 10 degree condition. But like I said earlier, I think what's happening here is that you have the muscle force coming down, but because of this change in the orientation of the ankle joint contact force vector, it's acting to cause no difference in this medial lateral bending moment about the tibia. Now, I think there's a reasonable complaint maybe to be made about this, that, okay, Michael, you looked at that everyone running across all of these grades at similar speeds, and maybe this doesn't really reflect how people engage with graded terrain when they're running outside. And I think this is a valid argument, but I also think that my results are fine. But there has been a nice study by Townshend et al. That showed that when people run outside, individuals may tend to speed up when they're running downhill, and they may slow down when they're running uphill. And I think for anyone who runs or who has spent any time running, this makes sense. But I think you can also kind of clarify the statement by saying, this isn't always true. When someone, there are certain inclines or there are certain lengths of hills where people won't change their speed. And I'll use an example. If I think about, I'm going to run from the top of Lady MacDonald, this mountain outside of Canmore. If I'm going to run from the top all the way to the bottom, I'm certainly not going to let myself just continuously accelerate as I go down this hill. Not only that would, first off, lead to a huge amount of muscle damage, but it's also just very uncomfortable. So I think whether an individual changes their speed depends on both the length and the grade of the hill. And in opposite to this, I think, some of you are able to understand this. For a short uphill, you can maintain a relatively similar speed. You just want to get the hill over with and get to the top. And this has been shown by Minetti et al., where they examined stair climbing, and they looked at when people were running up short flights of stairs, they would maintain the same speed as when they were running on level ground. But as the length of the stairs increased, they would begin to run slower and slower, because you have this change in oxygen deficit, where for a short hill, you don't really notice how physically exhausting it is, but as the hill gets longer, you do. So I think we can kind of modify maybe my statements. I think, it's reasonable to look at changes. I think it's reasonable to look at grade across using the same speed, but let's say my speeds are too slow. So in the downhill running conditions, everyone should just run a little bit faster to make up for the fact that maybe people actually do this. Okay, so how would my results change? Well, that means my results are likely underestimated. So the bending moments would be higher. But all this would mean is that, the internal bending moments would be no different than during downhill running than either the level ground or the uphill running conditions. And in opposite, if you say, okay, Michael, your speeds are too fast in the uphill running conditions. I certainly run slower when I run uphill. Well, what likely then is the case is that I've overestimated the bending moments. And in fact, maybe my results would be different, where you could say that, okay, if you slow down during uphill running, the bending moments might actually be lower than I'm actually presenting here, and they might actually be lower than they are in level ground running. Now, I kind of want to get back to this initial question I kind of teased you with. So we talked about these vertical ground reaction force parameters, the impact peak and the loading rate, and I said, look, a lot of people, this has been identified as a risk factor for tibial stress fractures, and people use this to kind of infer risk about tibial stress fracture in different conditions. But if you looked at the impact peak and the loading rate in downhill or graded running and tried to infer the risk of tibial stress fracture, you would end up at an erroneous conclusion. You would say that downhill running is certainly worse than level ground running or uphill running, because the impact peak and the loading rate is much higher. But this is not the case, as I showed you. Actually, downhill running appears to have slightly lower moments that are acting on the tibia than level ground or uphill running. And I think this finding provides further support to this idea that the ground reaction force, impact peak, and loading rate are poor surrogate measures of internal tibial loads. And if you really want to get an understanding of the forces and moments that the tibia is experiencing, it's worthwhile to go through these slightly more complicated modeling routines to actually get you a little closer to understanding how the bone is being loaded. And this will give you a little more validity in your statements about injury risk, perhaps, or just how the tibia is being loaded. So in general, that's kind of all I have for today, but I have one take-home message. I think, regardless of whether you have complaints about the running speed, I think incorporating graded running into a running program at least doesn't seem to change one's risk of developing stress fracture, or maybe not, it may not change one's risk of developing tibial stress fractures, because obviously it's a complicated scenario. But in general, it doesn't seem to be any worse than level ground running. And I think that's quite nice. So there's a few people I'd like to thank. I'd like to thank my supervisor, Brent Edwards, my co-supervisor, Guillaume Millet. I'd like to thank everyone in the Edwards lab who's provided tons of support throughout this. I'd like to particularly thank Gianluca Vernillo and Aron Martinez, who collected all of this data that I've been using. And I'd also really like to thank Tim Derrick, who has been really instrumental in helping me get through all of this modeling stuff and helping me, and who's really been a nice person to consult with about my findings. I'd be, if you want to find me on Twitter to ask me about anything, you can find me at the bottom too, and I'm happy to take questions now.
Thank you, Michael. I really enjoyed your talk. Before we get to the discussion period, I would like to gently encourage you to turn on your web camera during the discussion period if you are comfortable with it. Thank you very much. If you have any questions to our speaker, please use the blue icon raise hand button that can be found if you click the participants icon at the bottom center of your screen. You will see the icon labeled as raise hand button at the bottom on the right hand side. Now I'll open the seminar to the question. Yes, Art, please go ahead.
Thanks. I wanted to ask about uphill running. And I guess the reason is that I think most of us don't spend that much time running uphill or downhill. But one thing that people do often do in the in the gym is they'll run on treadmills that are inclined. So then they are spending considerable time running uphill. And also because of, I guess I would call it a factoid, which is people who have shin splints are advised to run on treadmills set on incline. And so, your results say that running on an incline doesn't matter, but what do you think of the factoid or the recommendation for people with shin splints?
Well, I think shin splints are a distinctly different injury from tibial stress fractures, and I wouldn't really group them in the same category. I think a lot of the time, there's two things. It depends kind of what people define as shin splints. I think of as shin splints as pain on the anterior tibia that probably primarily comes from this eccentric loading of the TA muscle. And I think in that case, because you have these, a lot of times you have changes in foot strike pattern when you run uphill, where you run more with a forefoot strike than a rear foot strike. I think that makes sense that you, in that condition, you might actually have kind of a lower eccentric load being placed on your TA. So I think in that case, if that's what they're talking about, then that might actually work.
Well, do you think you could show that in your calculations?
I think if I went back to some of the muscle forces, maybe, but at the same time, the static optimization isn't really designed. It's not really ever going to do a good job of estimating the tibialis anterior muscle forces because there's nothing that says it should produce a muscle force there. It only really is constrained to the joint moments, and there really isn't a joint moment in the TA except at the beginning of stance. If that's what's causing it, then maybe I could see a difference in these estimated muscle forces, and maybe then I could show something from the data. But at the moment, I don't have an answer for you, sorry.
Great, thanks.
Okay, Reed, please go ahead.
Michael, that was a really nice presentation. Okay, so I'm just going to start with a couple things here. So Townsend, we've published data. Runners don't speed up or slow down going uphill or downhill unless they're really tired. So we published a study a while ago showing that the range is 2.41 to 2.44 meters per second running uphill, downhill. I can point you towards that article, but
sure, yeah, that further supports my findings.
Yeah, no, that's why I bring it up. But that Townsend article is terrible because they just ran around a circuit 3 times.
Mm-hmm.
So in any case, okay, I'm really going to respectfully disagree with you though. There was a landmark study published in 1998 by Beck that discussed shin splints, more aptly named medial tibial stress syndrome, and it is a spectrum. So runners start with medial tibial stress syndrome or shin splints, which is more a colloquial term. than anything else. And that progresses to a stress reaction, that progresses to a stress fracture. So please don't talk about stress fractures as an independent, isolated event. It is a spectrum starting with medial tibial stress syndrome. Art is correct that one of the things that is, if people are on this end of the spectrum, if they are not at a stress reaction is kind of like the top of the bubble, and you don't want them to fall off and move towards a fracture. But my question here is, so I'm just stating that, and I'll really encourage you to not lump it in as an isolated event. In any case, tibialis posterior is really involved in medial tibial stress syndrome and stress fractures. So I'm curious how your model, I didn't see it accounted for, tibialis posterior specifically.
Yeah, the tibialis posterior is accounted for in the model through the ankle joint contact force. So since it crosses the ankle, this muscle would contribute to the ankle joint contact force, and ultimately this would contribute then to the bending and the force that the tibia is experiencing. Okay,
I just never saw its name pop up in the...
No, I mean, I didn't feel like it was necessary to present all of the muscles that cross the ankle joint. You know, that's something I could think about doing in future presentations. I just kind of assumed that the audience had a reasonable grasp on all of the muscles that cross the ankle joint.
Yeah.
But I would respectfully disagree with your statement about shin splints. I don't think there's enough evidence to support that it's a continuum. And in fact, I think that if it was a continuum, I think you would see far larger numbers of people with tibial stress fractures, because huge numbers of people develop medial tibial stress syndrome, but you don't see all of these people developing stress fractures.
No, I agree, because they self-regulate themselves and try to stay on this side of it. I will simply state, having run a sports medicine clinic for over 20 years, you're wrong. And I need you to open up your mind a little bit more in thinking about it.
That's fine, but I think you can also make the argument that these people don't have medial tibial stress syndrome, they have a stress fracture. And this is being shown in this nice study by Moen, where they look at these chronic cases of medial tibial stress syndrome, and they actually took bone samples from these individuals. And these look like stress fractures. You know, if you look at the histology of these images and you look at the histology that are taken from stress fractures, they look identical. So I think it's not that this is a continuum. I think in some cases, these are being misrepresented.
Well, I could point you towards hundreds of patients who have a positive triple phase bone scan, meaning that there is remodeling going on, but they have no pain, not significant enough to rate it as a stress fracture. So we can talk about this offline.
Yeah. You know, it's interesting because there's many things that are going on here. You could have a reaction that's occurring on the periosteum, but you know, this could simply be because of the muscle that's pulling on the periosteum, and maybe that's what you're seeing.
And that's tibialis posterior. It's either overcompensating for something, or it is too weak to do the job in the first place.
Sure, but I don't think that's the same etiology that's causing stress fractures.
Oh,
but you know, agree to disagree, I guess.
No, there's no agree to disagree. You're wrong on this, and I'm happy to talk about this afterwards.
We clearly should.
Happy to.
Okay, Brent, if you have a question to Michael.
Maybe it's just more of a comment that I disagree with Reed. There's absolutely no evidence to suggest it's a continuum. And if you want to have an HPL debate on something like that, it would be fine. No one ever talks about stress reactions of the pelvis, but stress fractures happen there all the time. Nobody ever talks about stress reactions of the medial femur. Stress fractures happen there all the time. Nobody talks about stress reactions of the dorsal surface of the metatarsal. They happen there all the time. So this is, I think it's maybe a logistical argument. If you look at the Fredrickson MRI scale, stress reactions tend to happen on the anterior surface of the tibia, sometimes the medial surface of the tibia. Grade 4s, which Fredrickson represents as stress fractures, tend to happen on the posterior surface. So I don't think it's as clear, cut and dry. You know, it would be fun to actually maybe just sit down and chat about it.
Okay, see. Thank you. I see Emily, you have a question to Michael.
Hi, Michael. Thanks for the good talk. Question about the model. Why do I see some papers on tibial bending estimate negative peak bending moments about the medial lateral axis? And what are they doing wrong or different in their models?
It could just be the convention that they're using, I think. But
that's interesting, because I think there's a discrepancy that I've seen in some papers that they then predict the negative moment, which is then tension on the posterior surface of the tibia.
Yeah, well, in that case, then their models would be wrong, since all the finite element models show that there's compression that's acting on the posterior surface of the tibia. Brent has many of these, and Efaz Hader from our group has a nice study as well looking at this. And we looked at this, and you see this in the obviously in this nice paper by Yang et al. I think where they looked at the in vivo deformations of the bone, and they see that the bone is bending in a way that would cause compression acting on the posterior surface of the tibia. So I guess if these modeling studies are suggesting that there's tension occurring on the posterior aspect, then yeah, maybe there's something that's off in their modeling approach. Off the top of my head, though, I can't remember though which ones you're talking about.
Yeah, we can chat more about it. I just agreed that I find it unexpected to see. So
thanks.
Michael, I actually also have a question, but this is more about the methodology. So when you collect your data, I think I might have missed, but what was your testing protocol? So I'm just curious if there is any effect of fatigue that might have affected your results.
Oh, the individuals only ran in each condition for about a minute.
Okay.
I don't think that's long enough for fatigue to develop. I think you need to run, fatigue probably develops pretty quickly in uphill running, but I don't think it develops that quickly.
I see. Thank you. Yes, Brent, please go ahead.
I would have waited. I just jump in because I have this burning question inside me. So you said a lot at the end about loading rates and how if you look at loading rate and you infer injury risk, then you'd be making a mistake. You'd get erroneous results because the normal stress data provide a different explanation. My point is that the people who believe that loading rate is responsible for stress fracture are not going to accept that argument because you're telling them that the normal stresses are higher, but they're going to say, I don't care about the normal stresses. I care about the rates of the normal stresses. So I think I know what you're trying to say. Of course, obviously, we've done a lot of research that shows that loading rate doesn't lead to more damage in the bone. And so I'm not going to try to make that argument. What I am going to make is that if you show a person that believes that loading rate is responsible for stress fracture and you say, well, look, loading magnitudes don't correlate well with loading rates, they're going to say, I don't care. It's the loading rate that does it. So you have to find a different way to make the argument.
Yeah, that the loading rate doesn't reflect the in vivo data. It's not, it kind of, I don't know. I mean, that's a tough one because you have to get into what is causing the stress fracture, right? Like, and I ultimately believe that it's the peak stress or the peak strain that the bone is experiencing. And, like we've talked about, that it doesn't seem that they have, that loading rate seems to play a large factor in this. Like all of the ex vivo data, especially the stuff that Lindsay did, seems to suggest this too. But okay. Yeah, there's probably a better way of phrasing it. I would agree.
Thank you. John, I see you have a question to Michael.
Yeah, great talk. I really enjoyed it. I've been thinking a lot about the inclines that people encounter in their normal training. And I have two little examples from a little research. So Heartbreak Hill at the Boston Marathon is about 2.5 degree incline. And the steepest incline you are allowed to encounter on a US interstate by law is about 3.5 degrees. So those are both much lower than the 5 and 10 degree inclines. So I guess obviously if you're running trails or something, like it's a different story. But I'm just curious if you think, if these findings also are applicable to people in that like more shallow range of inclines?
I think they're applicable, and I think they might also change a little bit. It kind of, I think, depends on how they adapt their gait to these conditions. In the more shallow uphill conditions, maybe the people would, I would need to check, but if the joint moments go up in these conditions, which I think they might if there aren't changes to their step length or their step frequency, which kind of would think to make sense if you're closer to a level ground running condition, then the joint moments might go up, and then the bending moments that the bone is experiencing might go up as well. And with the opposite, kind of what you see sometimes with downhill running is the grade steepens, people tend to shorten their stride a little bit as well. So the opposite might happen. Like if maybe they adopt a longer stride or they adopt the same stride, then maybe the joint moments would go up in the downhill running conditions. And again, then maybe the downhill running would just be closer to the level ground running conditions in this as well. It's interesting in the marathon perspective, we've been talking about downhill running in seminar a bit, and like Arash a couple of weeks ago made this great example of there's this kind of classic hill that I run down pretty often. And in Calgary, maybe it's that a lot of hills are actually pretty steep, that a lot of them are between, like it feels 5 to 10 degrees, like there's many that are kind of there. So I don't know, yeah, it's interesting to kind of, this would require a large survey across many different types of grades to really understand, or to really get an idea of how graded running affects the loading that the tibia experiences.
Okay, Benno, do you have any questions to Michael?
Yeah, nice talk. I enjoyed it.
Thank you, Benno.
I would like to make a comment about the loading rate. When I was still teaching 363, one of the examples that we did in that class was to estimate the loading at mid-tibia during a normal running step. And the interesting result that I remember from that time was that the loading rate was higher for the second half of the ground contact. The internal loading rate was higher for the second part of the ground contact than for the first part of the ground contact. And therefore, when you take the external forces, there the loading rate is highest at the beginning. So they are not related to each other. And that is another point why I would think that the statement that loading rate is not important is a good one.
Thanks.
That was a comment. Now, a question that I have: how confident are you about the estimated ankle joint forces? How big is the potential error?
Well, my results are similar to what other people have found, where the resultant ankle joint contact force is around 12 body weights. I think that static optimization provides generally a good estimate of the sum of all the muscle forces. But at the ankle joint, we don't have as much data as, say, we do at the knee joint, where they've implanted these telemetric implants. And that data suggests that you can actually get very good agreement between the contact force measured in vivo and the contact force measured in silico using a static optimization approach. I would expect then that you could get relatively good agreement at the ankle joint as well. But I can't have a sense of the error in my measurements, since I don't have a gold standard to measure against.
And how much are your results dependent on that force?
Well,
did you do a sensitivity analysis?
Because the results are between grade, it's more of the relative difference between the conditions. And I think that's pretty good. Whether or not the peak magnitude is correct, regardless of, let's say my peak magnitude ankle joint contact force is off by 2 body weights, I still think you would still get the same between condition differences in that scenario, and if you compare them to what I presented today. But I have not done a sensitivity analysis to see if this is true. This is just what I'm yeah, I think this would be the case just because of how the repeated measure design works. It's the
Okay.
relative differences that I'm interested
Thank you.
I still have a few more minutes for a couple of questions. I guess, yes, Walter, you have a questions to Michael? Sorry, I can't hear you.
Sorry, is this better?
Yep.
Yes.
Okay, sorry. You mentioned that you measured the stress about 1/3 distal on the tibia because the stress fractures occur there primarily. Why do they occur there? Do you have any idea? Is it because you think that the stress is actually greatest where you measure it there, or the bone is weakest and the stress are actually not greatest there? Or do you think it's a combination of the two, or why? Why does it happen there?
I think the stress and the strain seem to be the highest on the posterior aspect of that kind of distal third, the lower portion of the tibia. This is being shown by Brent and EFOS in a study that they presented last year. I think this is due to, maybe this is in part driven by changes in the geometry of the bone, where you can think it's really pretty wide up at the top, and it begins to narrow and become more slender as you approach the bottom of the tibia. And so it's this combination of, you have these forces, and you can have these big moments that are acting there onto a relatively kind of a more narrow cross section than at some other portions of the tibia.
When you showed the stick diagrams of the uphill and downhill running and the flat running, you showed that there were distinct differences in the knee joint angle and the femur alignment, but the footfall pattern seemed to be always very similar, and that really surprised me. Is that indeed the case, or did I misinterpret that?
I was trying to sort that out again, and that's actually from Arash's paper. So he would tell me, but the data is identical between the two. And I can present, here's some data. This is for all of the conditions, and this is the percent of the individuals who used a different foot strike pattern. And what you do see is when people begin to run uphill, they tend to adopt more of a midfoot to a forefoot strike pattern. This analysis was done by Marlene Giondolini using her kind of accelerometers based on the metatarsal and the heel of the shoe.
So how much would that affect your results, not only from the geometry, but that you actually use a potentially different footfall pattern for some of the runnings?
Well, there was a nice study by Rooney and Derrick a while ago that showed that the ankle joint contact force is higher in forefoot strikers than in habitual forefoot strikers than in habitual rear foot strikers. So I think that also contributes to the fact that maybe there's no difference in the internal moments between uphill running and level ground running. So if the contact force goes up, the bending moments that I presented would also go up.
And just for my own benefit, and maybe I missed it at the beginning, is there actually good evidence that downhill running results in more stress fractures than level or uphill running?
No, I don't think there is. The reason Brent and I became interested in this topic was from a paper by Charles Milgram, where they were looking at, interventions to reduce rates of tibial stress fracture in the Israeli military. And at one point they had kind of 40% incidence rate of stress fractures. So it was really high. And one of the changes that they made was they moved their base from a hilly location to a flatter location. And we thought, okay, maybe this is one of the reasons that it changed. The problem with that study is at the same time that they moved the base, they also reduced the total volume that the cadets were doing by 1/3. So it's a little trickier to find this. There's not good epidemiological, not that I know of, that there's epidemiological evidence to suggest that people who run on graded terrain develop more stress fractures other than that.
Great, thank you.
You're welcome.
Ross, if you have any questions to Michael?
Yeah, this will be fast. Just a suggestion based on Benno's question. I think when you go to publish this, I think something related to what he was asking about could be a likely thing a reviewer will ding you on, is, we need some validation here of the key input to the model beyond just the EMG, which is a little fluffy. I actually don't know of any instrumented ankle replacement contact forces. There's certainly none on ortho load. I just checked there, but you can find some studies of like cadaver simulated walking machines that do have at least some estimated like in vivo ankle forces there. And so that would at least give you something to compare to. And you're not going to get, running there. So, but you could at least like simulate walking in your model and show that it's close there. And maybe that's probably about the best you could do given the lack of data on that. I run into that with the knee too, where it's like, yeah, I'd like to validate contact forces running at 9 miles an hour, but that data is, not out there. So you look at walking and that's about the best you can get.
Okay, thanks for the suggestion.
This might be a good idea.
Yeah, I think it'll help.
Okay, Kun, I see you have a question for Michael.
Yeah, Michael, I was just wondering, so these results, I guess there are two things happening when you are running on an incline, potentially. And that is that you are running on an incline, so you are, let's say your leg moves, also moves vertically, basically, with respect to your forward progression, okay? But then the other thing that might happen is that when you're running on an incline, especially when you run on a treadmill, of course, your ankle angle changes together with the incline, depending on whether you have your heel on the ground while you are making contact with the ground or not, right? So during the step, you can either sort of walk on your toes when you're running uphill, or you can put your foot down flat. Now, what I've noticed from my limited experience of running and hiking here is that what I find super annoying about running on inclines or walking is in particular that my ankle feels flexed in an unpleasant way. And this particularly happens when you're running or walking on pavement, right? Because when you're walking in the mountains, I actually tend to put my foot down flat, even when I'm walking up, right? You tend to seek footholds, even when you're going up a steep incline, that put your foot down flat, which seems to be more pleasant. Can you comment on that? So to what extent is the effect that you're finding due to a change in the ankle angle, basically with respect to level, and to what extent will this be different when you are perhaps running or walking in a natural environment where you can choose to put your foot down flat often?
Yeah. I guess what I would need to know to kind of more answer that question fully is to get an idea of how, again, like the ankle joint moments are changing across these conditions. Because ultimately this is all, let's say, okay, maybe if it's basically like walking up a step, maybe then the ankle joint moment is no different, right? So it's
that's what I'm wondering. Yeah.
Yeah. I think that's one possibility. I think that during stair walking, it's more, there's no difference in the ankle joint moment. Maybe, to be honest, I'm not actually sure. I think there could be, depending maybe on where you place your foot on the stairs. I don't know. I think that's about maybe the best I can do. I think that when people walk uphill, maybe they tend to keep their foot flat. When I consider myself, when I run uphill, I think that I adopt more of a forefoot strike too, which kind of would dictate which would agree with my results. But again, maybe like if you don't do anything different, maybe the ankle joint moments stay the same, then you would have, let's say, you might have lower moments, right? Because that's really the moments dictate the muscle forces, and the muscle forces are really what dictate the contact force.
Okay, Walter, do you have any question?
Yeah, Mike, just a couple more questions. So, when you see the differences between uphill and downhill running in terms of moment, what would I have to do in order to change speed to kind of cover that range of, because 10-degree downhill and 10-degree uphill is quite enormous. Would I have to go through an enormous speed change to get that variety of moment changes, or would it be relatively small?
Are you asking whether the moments change substantially in the two conditions relative to the other one, or are you asking how would you get equivalent moments in graded running as opposed to a level?
Exactly. How would you get equivalent moments by speeding up or slowing down on the flat? Or in other words, are these moments very, very sensitive to speed?
Yeah.
And therefore, how fast you run might be more important. You know, if they're very sensitive, then how fast you run might be much more important in terms of loading than whether or not you run a little bit uphill or downhill.
Yeah, the speed definitely plays a big part. I also, you know, and the speed thing is also, you can also think about that the step frequency changes as people run uphill. They tend to adopt these short, fast strides. It's kind of like going up the stairs, where you prefer to take stairs one at a time as opposed to two at a time. So in this analysis, what I did here was I looked at people running with their normal stride frequency in 10 degrees, and then I looked at them running with 10% less preferred stride frequency. So basically what I'm trying to do is replicate the stride frequency they would use in level ground running. And what you can see is that the ankle joint contact force is, you know, still a little bit lower. So
but you did not look at different speeds of running and see how that changed at the moment.
No, but I would expect that if you changed the speed of running, like if you run faster uphill, the moments will have to increase, and this would then result in larger bending moments being placed on the tibia. And the same thing going downhill, I think. I think if you run faster downhill, the moments will probably get greater as well. Whether that's driven, you know, there is a question of how the distribution would occur though. Like maybe when you run faster downhill, the increase in the joint moment primarily occurs at the knee, right? Because it's, you're trying to absorb a lot of energy, and that occurs primarily during downhill running the knee. But if I recall, I think in some studies I've seen that the ankle joint moments also tend to increase in downhill running when you run faster too. Actually, Arash has showed this.
I was just wondering if your results are maybe true very specifically for 3.3 meters per second running. And if I did it at 1.5 meters or at 5 meters, they might actually be conceptually different.
Yeah, I think that's what I tried to highlight at the end, I guess, with my speed discussion, where I think, like, if you tell me, you know, if you think that my people run slower uphill, then yeah, the bending moments would be probably lower than they are in level ground running. And then the opposite would occur if you believe that people run a little bit faster on downhill running, then probably the differences that I saw wouldn't be as great. So downhill running wouldn't look nearly as good in comparison to level ground running.
But if you ran at the same speed, let's say you did the exact experiment again, but at half the speed, you know, 1.6 meters per second, or at 4.5 meters per second, you would think that the relative differences in what you found conceptually would hold true.
I think so. I would like to think so, but I should probably do that just to check. It'd be nice to have a better understanding of how kind of the, if I really want to understand, or we really want to get an idea of how the tibia is being, you know, bending, or it's being loaded during locomotion, we need to do those types of experiments too, to really kind of, you know, cover the whole scope of speeds and grades that people can, that people use.
Lots to do.
That's good for me. I have a long time left in this career, I hope.
Yes, John, if you have any questions to Michael.
Oh, this is just a short tack on to that last question. I'm reminded of this series of papers on graded running, kinematics and kinetics that came out this year. And I think they found significant interactions between speed and incline on kinetics. So there might, like you said, more work to do, and there might be differences that depend on the interaction between speed and incline.
Yeah, that I think what's happening there is that you kind of maximize, like when you're trying to run fast uphill, you know, people generally try to lengthen their step first when they do it on level ground running. But when you run uphill, you can't employ the same strategy because you have this kind of barrier, right? You need to then, what you tend to do first is you actually tend to increase your step frequency over this other choice of lengthening your step. That's actually what, I'm a co-author on those papers, so I should know the results.
Okay, would there be any final question or comments for our speaker? Yes, Ryan.
Hey, Michael, great job. I'm curious about the idealized cross-section of the tibia. And I'm wondering what ideas you have on trying to improve that approach when calculating the bending moment.
Well, Brent and I were chatting about this yesterday, I think that this works okay. It works pretty well in these kind of repeated measures designs. I think probably how this is going to move forward though is looking at doing some kind of shape modeling, maybe really the limitation here is that it's symmetrical, right? And the tibia is not. The tibia is very asymmetrical. And that's what I was kind of getting at. Like the normal stress equation gets much more complicated when you have an asymmetrical cross section, because obviously the moment of inertia is not equivalent kind of everywhere. So maybe like, I don't really know. I'm not sure. Maybe this is the limit of kind of the idealized ellipse or these simplified models. But I think, and I know that there are some groups who are looking at kind of doing statistical shape modeling to get better estimates of tibia geometry from very sparse data. And maybe that's how we take this one step further. So instead of requiring everyone to get a CT scan, we can use these shape modeling approaches to approximate their individual geometry. And that would get better stress estimates, I think. Well, it certainly would get better stress estimates. Yeah, that's about all I can I hope that answered the question. If it didn't, please tell me.
Okay. Yes, Walter.
Just a quick comment before we go to song one, really to you. Let's make sure that we don't forget that Reed and Brent wanted to do a debate on stress fractures and how they occur in the next semester.
Well, do you want me to organize things?
Did I say next semester?
Well, that's what I said.
I think that would be great.
Debates. I thought that would be a great debate. So let's do it if there's time.
Okay, I'll find a spot, maybe one seminar, and then I'll let you know.
The debaters.
Okay, on that note, I would like to thank Michael again for sharing his work with us. Before we wrap up this seminar today, I would like to make a couple of announcements quickly. So today's seminar is the last one for this year, 2020, and the next seminar will be on January 14th. We will keep the seminar online via Zoom and with the same Zoom link that we've been using, and I'll be sending out a reminder in early January. Also, all previous presentations for this fall in the HPL seminar have been now all uploaded on our website under Biomechanics Seminar Series. So whoever wanted to go back to the previous discussion or presentation, please feel free to find and watch them. I hope you have a nice and warm holiday, and I'll see you next year. Happy holidays.